Welcome to Day 10, Equations Involving Trig Functions. You will need the 3 P's, a pencil, paper, and patience, as well as a graphing calculator. In today's lesson, we are going to talk about solving equations that have trigonometric functions in them. As with our lesson from Day 9, we should visualize the function of theta in our equations as the variable of the equation. If we can do this, we can manipulate the equations in the same manner as an equation involving a variable such as x or y. We will also be told to solve within a domain. In other words, we're asked to find the values of theta that will make the equation true in the given interval, usually from 0 to 360 degrees or from 0 to 2 pi radians. In order to solve these problems, we will follow 4 basic steps, 2 of which we already know from Day 6 and 7. We start by solving the equation for the given function of theta. In other words, we isolate the function of theta and place everything else on the other side. Second, we solve for the reference angle by quote-unquote solving for theta, either by using our chart of known values or using the corresponding inverse trig function. So, for example, if I have cosine of theta equal to some value, in order to find theta, which will be my reference angle, I need to take the inverse function of both sides. Theta will be equal to the inverse cosine of the given value. In step 3, we determine the quadrant the reference angles will be located in based on the positive or negative value of the function of theta. Finally, in step 4, we calculate the values of our theta that will satisfy the equation the same way we did on Day 6 and Day 7. Now, let's take a look at some examples and practice our technique. In example 1, we are asked to find theta to the nearest degree on the interval 0 to 360 degrees. What we should notice is that cosine of theta is my variable in this equation, and in your mind should look similar to the equation 4x minus 3 equal to 4. Seeing this parallel, I know I can solve my trig equation in a similar manner by isolating cosine of theta. I do this with simple arithmetic, adding 3 to both sides of the equation, and then dividing a 4 from the result, leaving a final equivalent statement of cosine theta equal to negative 1 over 4. This new equation looks like our equations from Days 6 and 7. I see that the value of cosine is negative, so I know that the graphs of the angles I am looking for will be in quadrant 2 and quadrant 3. I can show this by drawing my quadrants, adding sugar to coffee, and seeing that the angles must be in 2 and 3 where cosine is not positive. Next, I need to determine my reference angles. To do this, I take the inverse cosine of both sides of my equation. On the left, cosine and inverse cosine cancel out, leaving theta, and on the right, I am left with the inverse cosine and the positive value 1 over 4. Remember, I take the positive value here because I am searching for a reference angle, and a reference angle is always a positive value. If I plug this statement into my calculator, I get a decimal value which I round to the nearest degree, 76 degrees. This is the value of my reference angle, which I can now use to find my angles in quadrant 2 and 3. These angles will be values of theta that satisfy the original equation on the given interval. Using my quadrant operations, I find the value of theta in 2 to be 104 degrees and the value of theta in 3 to be 256 degrees. In example 2, I'd like you to pause the video and try to solve this equation for the function of theta. Go ahead and pause the video now. How did you do? Compare your answer to the one on the screen. Once you have reached this point, you can proceed as we did in example 1 to find the reference angle, and from there find the angle values of theta that will satisfy this equation. I start by drawing my quadrants and realizing the value for sine of theta is positive. This means the angles that I am looking for will be in quadrant 1 and quadrant 2 where the sine function is positive. Now I want to find my reference angles. If you remember your chart, you know that sine is equal to radical 2 over 2 when the reference angle is 45 degrees. If you don't remember, you can also take the sine inverse of both sides to reach the same answer. Now we can easily find our values of theta with theta in 1 equal to 45 degrees and theta in 2 equal to 135 degrees. However, I am not done. I realize my interval is in radians, so I must have angle values in radians. I multiply both my angles by the conversion factor, pi over 180, and get the radian values for my angles as shown. In example 3, because we do not have an equation initially set to 0, we must manipulate the equation so that one side is equal to 0. We do this by subtracting cosine theta from both sides. This gives us cosine squared theta minus cosine theta equal to 0. Remember, we can do this because we are looking at cosine theta as our variable, and just as if it were the variable x, we can subtract it out from both sides. We are now left with an expression on the left which can be factored. In your mind, you should see a parallel with x squared minus x equals 0. Here the common factor is cosine, so we pull it outside and are left with the given statement. Note that we now have two factors multiplied together set equal to 0. As in algebra, we set each individual factor equal to 0 and solve from there. On the left, we should notice that we have two values of theta that will make this statement true, i.e. theta equal to 90 or 270 degrees. On the right, we get cosine equal to 1, and notice that once again we have two values of theta that will make this true, i.e. 0 and 360 degrees. Once again, we are not done. Because the interval is in radians, I must convert my angles to radians as shown using the conversion factor. What I notice is that 2 pi is not included because the interval is less than 2 pi, so we reject that value. Your answer should now consist of the remaining 3 angles. In example 5, we notice we have a quadratic trinomial with a coefficient of the squared term that is not 1. For the purpose of this lesson, this means we are going to use our funky factoring method. In your mind, you should think of the equation with x in place for cosine theta, paralleling the equation 5x squared minus 14x minus 3 equals 0. Since our trig equation is already set equal to 0, we can start by labeling our coefficients a, b, and c respectively, and drawing two sets of parentheses for our factors. To begin factoring, the first term in both sets will be the coefficient a times the variable, in this case 5 cosine of theta. Next, multiply your a and c terms to get negative 15. We think, what factors of negative 15 will add to our b term, negative 14? This is obviously 1 and negative 15, which we place in our sets alternatively. To complete the factoring, I ask if any of the terms in the sets have common factors, and if so, divide them out. The left set has common factors of 5, so we divide it out and rewrite our final factors and set them equal to 0. Now we can proceed as in example 3 by setting each factor equal to 0 and isolating the function of theta. On the left, when I isolate the function, I get the result cosine of theta equal to 3. Now take a look at what happens in your calculator if you try to solve for theta here. Remember, to solve for theta, I will have to take the inverse function of both sides, in this case, the inverse cosine. However, when I plug the inverse cosine of 3 into my calculator, it gives me an error message about the domain. This is because of a particular rule of sine theta and cosine theta you must know from now on. That is, that the value of either of these functions cannot be greater than 1 or less than negative 1. Because cosine theta equals 3 here, we reject this answer as false and move on. On the right, we solve as we did in example 3. Isolate your function of theta, and you should get a result, cosine theta equal to negative 1 over 5. Now draw your quadrants, and notice that the cosine of theta here is equal to a negative value, meaning that the angles which will satisfy my original equation will be in quadrant 2 and 3, where cosine is negative. To get the reference angle, take the inverse cosine of both sides of your reduced equation. This should give you a value of theta equal to 79 degrees when rounded to the nearest degree. We can now use this reference angle with our quadrant operations to find the angles we are looking for. Here, theta in 2 should equal 169 degrees. and theta in 3 should equal 259 degrees. Your final answer should consist of two values of theta that will satisfy the original equation. Here are the skills that you should be able to do. If you are having trouble, replay the video and focus on the skills you are struggling with. Until next time, this is Mr. Mackman signing off.